Hello everyone. In this video and in the next videos, I'm going to show you how to put artificial intelligence on an Arctic 7 FPGA. More specifically, I'm going to show you how to build a feed-forward neural network that classifies MNIST digits in real time. What you're seeing right now is the end result. I wrote a custom Python program where I type in a number to pull up an MNIST image. When I close the image window, the program streams that image over a physical wire into the FPGA using UART. Once the full image has been received, the FPGA runs the network, makes a prediction, and displays the result on the 7-segment display. And as you can clearly see on the screen, the accuracy is high. Each time I transmit an image, the AI model on the FPGA is able to correctly classify it. This simple network reaches about 99% accuracy on the MNIST dataset. This project originally came from my master's thesis. And in this series, I'm going to walk you through how to build the entire AI accelerator from start to finish. To keep this series from turning into a multi-hour lecture, I'm going to focus on only the most important concepts at a high level. If you want the full source code and lower level implementation details, you can get them through my book, Verilog Based Robotics and Signal Processing. There's an Amazon link for a physical copy and a Stripe link for a digital copy. Also, as a quick reminder, this video is part of a full course based on the book. If you want to master real Verilog-based digital design, then this course and book are for you. In this video, we're keeping it simple, with no Verilog yet. We're just going to go over how a feed-forward neural network works. We'll go over the neuron math, how neurons get grouped into fully connected layers, why we use ReLU, how an image gets flattened into an input vector, and how to interpret the output when the network makes a prediction. Then in the next video, we'll start implementing the math and hardware using Verilog on the FPGA. So to start, let's talk about what a neuron actually is. A neuron is the basic building block of a feed-forward neural network, and a feed-forward neural network, or FFN, is basically the simplest kind of neural network that you'll see in machine learning. Mathematically, a neuron takes in a vector x, it has a weight vector w, and it has a bias vector b. Then it produces one output number. And the computation is very simple. You take the dot product of x and w, and then you add the bias b. So the output number is x dot w plus b. So that's it. That one operation is the entire job of the neuron. Alright, so what is ReLU? Well, ReLU is a simple math operation we apply to the output of a neuron. It's called an activation function. And the reason we use it is because it introduces nonlinearity, which is what lets neural networks model more complex relationships than just a giant linear equation. ReLU takes in a single value and it outputs a single value. And in any typical feed-forward neural network, the output of each neuron feeds directly into a ReLU block right after it. ReLU is defined as the maximum between 0 and the input of ReLU. So in plain English, if the neuron's output is positive, ReLU leaves it alone. If the neuron's output is negative, then ReLU clamps it to 0. And if you don't see ReLU in a network, it's not that nothing is happening, it just means that a different activation function is being used instead. So this is how you assemble a bunch of neurons to make a feed-forward neural network. Each column of neurons is a layer, and within a layer, every neuron receives the same input vector, but each neuron produces a different output because each one has its own unique weight vector w and bias b. All of the neuron outputs in a layer get grouped together to form a new vector, and that vector becomes the input to the next layer. So a clean way to think about it is this. Each layer takes in a vector and produces a new vector, and the way it produces that new vector is simple. Each neuron computes x.w plus v, and the collection of those results becomes the layer's output vector. So this slide is still the exact same idea, it's just drawn in the most common way that you'll see in school, papers, and in industry. And honestly, this style is less intuitive than the version I just showed you because it hides a lot of the structure and just shows circles and arrows. But regardless, this is the standard notation, so it's important that you're fluent in it. The key is to know that when you see a diagram like this, it's just another way of representing the same vector-based layer behavior that we already covered. So how do you feed an image into a neural network? Well, you don't feed it as a 2D grid, you flatten it into a single 1D vector, and that vector becomes the input to the network. For MNIST specifically, the image is 28 by 28, so that's 784 pixels total. When we flatten it row by row, the first row becomes elements 0 to 27, the second row becomes 28 to 55, and that pattern continues until the last pixel becomes element 783. So after flattening, the image is literally just this vector, P0, P1, all the way to P783, and that's what gets streamed into the FPGA. So now let's talk about how to interpret the output of a feed-forward neural network. An FFN takes in a flattened input vector, which we've been calling X, and it produces an output vector C. The key idea is that the length of that output vector is equal to the number of classes that the network can predict. Each element in C is just a score that represents how confident the network is about a particular class. To make a prediction, you don't do anything fancy. You simply compare values in C and pick the index of the largest one. That operation is called argmax, and the index of the largest value is the predicted class. For example, if a network is trained to classify images as cat, dog, or neither, then the output vector C will have 3 elements, C0, C1, and C2. If the network outputs something like 0.2, 1.7, and negative 0.4, then C1 is the largest value, so the network predicts whatever class is assigned to C1. And this last part is really important. The meaning of each output index is something you choose during training. You get to decide what C0, C1, and C2 represent when you label the data. One model might map C0 to cat and C1 to dog, while another model might use a completely different ordering. The network does not know or care about the labels themselves. It just learns the mapping you trained it with. So when you interpret the output, you always use the same class mapping that was defined during training. So that's the core idea behind how a feed-forward neural network works. At the end of the day, everything reduces to one operation, evaluating a neuron, and a neuron is just a dot product plus a bias. If you can design hardware that multiplies 2 vectors, accumulates the sum, and then adds one constant to the end, you've already built a huge chunk of what a FFN is doing, because the network is really just that same computation repeated across many neurons and across multiple layers. In the next video, we'll start making this in real hardware. We'll design the circuitry needed to evaluate a single neuron, and I'll walk you through the key design choices so you get a solid intuition for what it takes to implement this on an FPGA. That's it for this video, and I'll see you in the next one.